need to expose image processing to your AI with precise control over parameters like dimensions and output formats. You'll see how to create a FastMCP tool that handles image URLs, optional resizing with pixel constraints, and format selection, all with automatic validation and clear documentation for the AI client. From typing, import annotated. From Pydantic, import field. At MCP, tool. Def process image. Image URL. Annotated SDR, field. Description equals URL of the image to process. Resize. Annotated bool, field. Description equals whether to resize the image. False. Width. Annotated int, field. Description equals target width in pixels. G equals 1, L equals 2000, equals 800. Format, annotated. Literal, JPEG, PNG, web. Field, description equals output image format. Equals JPEG. Dict. Process an image with optional resizing. Hash implementation. This demonstrates the declarative tool pattern for exposing Python functions as AI callable capabilities. The @MCP tool Decorator transforms ordinary functions into self-describing RPC endpoints, where type annotations and docstrings become the API contract. What makes this distinctive is how it bridges Python's native type system with external tooling protocols, eliminating the need for manual schema definitions or transport layer code. The pattern works by treating functions as pure business logic, while the decorator handles protocol concerns. FastMCP introspects the function signature at runtime, converting type hints into validation rules and generating open API-like schemas automatically. This separation means your implementation stays clean, focused on the what, while the framework manages the how of exposure, validation, and transport. This approach solves the boilerplate problem in RPC development, particularly for AI integrations where tools must be discoverable and type-safe. It's ideal when you need to expose backend logic to external systems without writing custom API layers. The trade-off is framework coupling, but the benefit, reducing hundreds of lines of transport code to a single decorator, often outweighs it for tool-heavy applications. Let's break it down line by line. From typing, import annotated. Imports annotated from Python's typing module. This enables adding metadata to type hints, which FastMCP uses to generate tool schemas and documentation from your function signatures. From Pydantic, import field. This imports field from Pydantic, which enables fine-grained schema control for function parameters. It lets you add descriptions, validation rules like g/la, and default values, critical for AI tool schemas where precision matters. At MCP, tool. Def process image. The @MCP tool decorator marks this function as an AI callable tool. It transforms the Python function into a structured API endpoint that AI models can invoke, using the type hints and docstring to generate the tool's schema automatically. Image URL. Annotated SDR, field. Description equals URL of the image to process. This defines the required image URL parameter using Pydantic's annotated type for runtime validation. The field description becomes the AI tool's documentation, ensuring clear usage instructions for model callers. Resize. Annotated bool, field. Description equals whether to resize the image. False. This defines an optional Boolean parameter that controls image resizing, defaulting to false. The annotated type with field description makes this parameter self-documenting in the AI tool schema, ensuring clear usage instructions without additional code comments. Width, annotated int, field. Description equals target width in pixels. G equals 1, L equals 2000, equals 800. This defines an optional width parameter with runtime validation. The G equals 1, L equals 2000 constraints enforce valid pixel dimensions, preventing invalid resize operations while defaulting to 800 px for convenience. This is Pydantic's field validation pattern, ensuring type safety and business rules in one declaration. Format annotated. This defines a constrained string parameter using Python's literal type, limiting the format argument to only JPEG, PNG, or WEP. The type system enforces valid image formats at call time, preventing invalid values from reaching the implementation. Literal JPEG, PNG, WEP. This uses Python's literal type to restrict the format parameter to only JPEG, PNG, or WEP. It enforces type safety at development time, preventing invalid image format strings from being passed to the function. Field description equals output image format. This adds metadata to the parameter, creating self-documenting tools. The description appears in AI tool schemas and generated documentation, eliminating the need for separate docs. Equals JPEG. This sets JPEG as the default output format using Python's default parameter syntax. It ensures the function always has a valid format value, eliminating the need for additional validation when no format is specified. Dict. This return type annotation declares the function returns a dictionary. It enforces type consistency for AI tool responses, ensuring the output matches what callers expect and enabling proper schema generation for the tool interface. Process an image with optional resizing. This docstring defines the tool's purpose for AI models and documentation. It becomes part of the tool's schema, ensuring clear usage instructions appear in both the API reference and AI interface. Hash implementation. This placeholder marks where the actual image processing logic would implement the function's contract. The implementation would handle downloading from the URL, optional resizing to the specified width, format conversion, and returning the processed image metadata as a dictionary. FastMCP tool schema design. The annotated type with Pydantic's field creates self-documenting tools where validation rules become part of the function signature, not separate documentation. Validation constraints like G equals 1 silently enforce boundaries that clients never see as errors, only as natural limits. This pattern turns type hints into living contracts between your code and AI models.
The schema that describes everything must itself remain invisible to be understood.